In this video, I will go over the homework 13.2 that follows the lecture called Improper Integrals of Type 2. And as always, I hope that you watched the lecture. And let's go ahead and jump right into the homework. And in this homework, we are dealing with integrals of with improper integrals of type 2. And what makes an integral improper and of type 2 is the fact that there is a point of discontinuity somewhere on the interval of integration, which means the function cannot be evaluated around that point, assuming that it is continuous. So here we have a rational function, and it is very easy to see that the function is not defined at 0. That means we are going to have to split the integral at 0 using the subdivision property of integrals. And now that we have two integrals, each of them is also improper, but can be easily taken care of by simply introducing a variable and replacing the limit of integration at which we have a problem with continuity with that variable, and sending that variable to the point from the appropriate side. So from -6, we're going to approach to 0 from the left, but we're going to start from 0 on the right side to go to 1. So s approaches to 0 from the right side. But the integrand is the same. And the next step is to actually find, so we're going to kind of hit the pause button here, and we're going to try to find this general antiderivative of this function. And to do so, we're going to rewrite it, and then we're going to use the power rule. So it's going to be -5/4 x to the power -4. So now we're ready to put it back into the original integral. So let's continue with the main solution. So the first one is the limit as t approaches to 0 from the left side. And we have -5/4 x to the power -4. We're evaluating it between -6 and t, plus we have limit as s approaches to 0 plus of -5/4 x to the -4 from s to 1. Now, by the fundamental theorem of calculus, the first integral evaluated at t is this, and evaluated at -6 and the second one evaluated at 1 is just -5/4, but evaluating it at s gives us this. And And you can see that when t goes to 0, this goes to negative infinity, and this goes to positive infinity, but those infinities do not cancel one another, so the integral actually diverges. The reason is that in order for the original integral to converge, both parts of the sum have to converge. So we're gonna input the does not exist answer. Let's move on to the next problem. We have some trigonometric integral from pi over 3 to pi over 2 to secant squared 3x dx, and we know that secant function is not continuous at 0. It's continuous, so pi over 2, I guess. Is it pi over 2? Secant cosine of pi over 2 is 0, so secant doesn't exist. So here we have a problem with the upper limit. So we're going to replace the upper limit pi over 2 with the new variable t, and we're going to approach t to pi over 2, but from the left. Now, to do this problem, we're going to introduce a linear substitution. So t is not a good choice because we're using t as a variable of in the limit. So let's introduce letter s. So s is 3x, ds is 3dx. So dx will be 1/3 of ds. And we still have a limit. Limit is now the problem, and integral is just a problem within a problem. So we have a new integral. We don't know the limits of integration, so from a to b we have 2 secant squared 3x, that's s, and instead of the x we're going to write 1/3 ds, and this 1/3 and this 2 don't affect the integration, so we can just write it out 2/3. We can take it outside of the integral and the limit, and antiderivative of secant squared, I believe it's tangent s, but s is 3x, so we can just write tangent 3x. And since we already went back to the original variable, we can put the limits of integration from pi over 3 to t. So we have 2/3 limit as t approaches to pi over 2 from the left. So we have tangent 3t minus tangent 3 pi over 3, so it's tangent pi. So tangent pi is 0. Tangent 3 pi over 2 is equal to sine 3 pi over 2, which is 1, or the negative 1, over cosine 3 pi over 2, which is 0. So we have negative 1 divided by 0, and we don't have to really get involved into the signs, whether it's plus or minus infinity. That's what we learned. That's going to be enough for us to conclude that the integral diverges. All right. Problem number 3. We have integral from 0 to 4, x cubed ln 2x divided by 4 dx. The integral is not defined at 0. So let's do some basic maintenance. Let's take out the 4. Let's, in the integral, replace 0 with t. And let's send t to 0 plus. So what we have left is that. But that looks like a standard problem for integration by parts. So I'm going to set it up as integration by parts. U is ln of 2x, dv is x cubed dx, so du will be 1 over 2x times 2, so it's just going to be 1 over x dx, and v will be 1/4 x to the power 4. So now we're going to continue with the integration process. We have 1/4 limit as t goes to 0 from the right side. And now instead of the integral, we're going to start writing the integration by parts steps. So we have 1/4 x to the 4 ln 2x minus, and we need to start plugging in the limits. So it's going to be from t to 4 minus integral of v du, so it's going to be 1/4. It looks like we have integral of x cubed dx. So we have a lot of 1/4 there. I'm going to take that 1/4 out. So now we have 1/16 limit as t approaches to 0 plus. And we have, so now I'm plugging in 4. So 4 to the power 4 ln of 8 minus t to the 4 ln of t, 2t, minus, so we have 1/4 x to the 4 from t to 4 and continuing. So we have 1/16 limit as t approaches to 0 plus. We have, I think I'm just gonna wait. So here we have 0 times infinity, so we're gonna address that by using the L'Hopital's rule. But besides that, we have 1/4 times 4 to the power 4 plus 1/4 t to the 4. So t to the 4 goes to 0. 1/4 of 4 to the power 4 is just 4 cubed. But for everything else, we have to use the L'Hopital's rule. So the answer will be 1/16 limit as t goes to 0. We have 4 to the power 4 ln 8 minus 1 over t over 1 over, so here we have, I guess there's no benefit in writing it as 1 over t to the 4, but rather it's t to the negative 4. So if we write it as -4 times t to the -5 and that's division, so it becomes positive 5, so it's t to the 4, so this whole thing goes to 0 as well. And the only thing that's left really is we have 1/16, so it just takes away 2 powers of 4, so we have 4 squared ln 8 minus 4. So 16 ln 8 minus 4. I'm not sure how I feel about this answer, but let's try. 16 ln 8 minus 4. And that's the correct answer. Let's do another problem. It will be number 4. So I have an integral from -4 to 6. And this particular integral has a problem at 6 because integrand is not defined at that value. So we're going to address the problem by introducing a new variable, let's say t, and setting up this problem as a limit as t approaches to 6 from the left. And we have 1 over square root 6 minus x dx. And I'm going to do the substitution here. So we have, so substitution will be s is equal to 6 minus x. So ds is equal to negative dx. And the integral now becomes, it's still the limit as t approaches to 6 from the left. Since we're doing substitution, I'm not gonna worry about the limits of integration, but we have 1 over s, and dx is equal to negative ds. So I think we can take that negative out, or we can just keep it and conclude that the antiderivative is negative ln of s, but s is 6 minus x. And now that we went back to the original variable, we can plug in the original limits, which were -4 and t. So let's plug in t. So we have negative ln 6 minus t minus negative, it becomes positive, ln 6 minus -4. Now, ln of 6 minus -4, it's just a fixed number, but plugging in t equal to slightly less than 6 will give us ln of 0 here, and ln of 0 is negative infinity, but negative times negative is positive. So because it's not a finite number, we conclude that the integral diverges. And that's the answer. Oh my god, that was a silly mistake. I forgot the radical here. Great. So, great catch. I cut it myself, I guess. So, the antiderivative of square root of 1 over square root of s, I believe it's going to be, let's do the math here, s to the power -1/2. So it's just going to be 2 square root of s, but s is 6 minus x. And we had that negative there, so it's going to be negative here. So let me rewrite everything. So we have -2 square root of 6 minus t plus 2 square root of 6 minus -4. So this goes to 0, and this goes to 2 square root of 10. So let's try this again. This time I'll be a little bit more careful. I'm not going to rush. So I may also want to try and see what Desmos would do. And it just doesn't hurt to try. Integral from -4 to 6 of 1 over square root of 6 minus x dx. So it seems like it converges. We just need to make sure it converges to what we think it converges. And it does appear so. So I'm pretty sure that this answer is correct. So the type of mistake I've made could have been easily avoided, but it just doesn't hurt for the sake of practice. For the sake of practice, to see how mistakes are addressed. Because it's inevitable before you make one. Anyway, if you have any questions about how to solve improper integrals of type 2, please let me know.